This video presents DeepLiDARFlow, a deep learning architecture for scene flow estimation using monocular camera and sparse LiDAR. The corresponding paper was presented at the International Conference on Intelligent Robots and Systems in 2020. DeepLiDARFlow utilizes sparse LiDAR measurements and image features for dense scene flow estimation. The network extracts features in a hierarchical way and fuses the LiDAR and RGB information in a multi-scale deep fusion. The solution is computationally efficient, robust and improves the localization of features. We assume that LiDAR frames are well calibrated and synchronized to the monocular camera. Our network consists of a feature extraction block which uses feature pyramid networks to compute LiDAR and RGB features separately, a multi-scale fusion block for merging both features, a multi-scale scene flow prediction, and a context network to refine the final estimate. There are two different streams for feature extraction streams. One for RGB and another for LiDAR data. Both streams consist of 6 encoder blocks and 5 decoder blocks. For the RGB stream, we use multiple convolutional layers at each scale. The LiDAR stream uses confidence convolution layers. The RGB features, LiDAR features, and confidence maps are fused at each scale. For fusion, the depth features are refined in a series of convolution layers and then concatenated with the RGB features and the confidence maps. The concatenated features are further refined by 4 convolutions. The fusion network assists in propagating the sparse depth information to full image resolution and enriches the RGB features with geometric information. Then the fused features will be forwarded to the scene flow module. Scene flow is predicted at each scale, from coarsest until finest. The previously estimated scene flow is used for warping, before a cost volume is constructed. The cost volume along with the warped and reference features is the input for actual scene flow estimation. The prediction at the finest resolution is further refined by a context network. Here is a visual comparison between our approach and a learning-based method that utilizes RGB only. Our network fuses just 5,000 LiDAR points with a half-megapixel image. DeepLiDARFlow can estimate scene flow more robustly, especially for dynamic objects. This is best seen by comparing the error maps. We notice as well that our DeepLiDARFlow predicts edges more precisely, in other words with better localization. Quantitatively, we compare to different sensor modalities, PWOC3D, which uses a stereo camera, LiDARFlow which fuses a stereo camera and a LiDAR sensor, and a monocular versions of LiDARFlow. We analyze the realistic scenes from KITTI and the synthetic scenes from FlyingThings3D. Again, 5,000 sparse LiDAR points are used for the fusion. The robustness under varying number of LiDAR points is tested too. DeepLiDARFlow shows competitive outlier rates and superior endpoint error even for as little as 100 sparse LiDAR measurements. In comparison to a state-of-the-art approach that uses LiDAR only, we demonstrate how important fusion is to achieve high robustness. LiDAR measurements that belong to the street surface have been excluded in this comparison as a necessary requirement of the LiDAR-only approach. Quantitative results confirm that the fusion is important for robust scene flow estimation of the entire scene in a single pass. Thank you for watching our video.